Hi, my name is Jesse Goodman. I'm a PhD student at Cornell, and today I'll be talking about extractors and secret sharing against bounded collusion protocols. This is joint work with Eshan Chattopadhyay, Vipul Goyal, Ashutosh Kumar, Shin Lee, Raghu Meka, and David Zuckerman. The primary object of study in this work are bounded collusion protocols, or BCPs. These belong in the world of communication complexity, and so we'll start by talking about what communication complexity is. In particular, we'll recap the NIH and NOF models. Then, once we know what BCPs are, we'll begin by stating our main theorems. Our first main theorem establishes explicit lower bounds against BCPs. Our second main theorem establishes an object called a leakage-resilient extractor against BCPs. And our third main theorem constructs so-called leakage-resilient secret sharing against BCPs. And we'll get into what exactly these things are. Turns out that extractors against BCPs are just strong average case bounds against BCPs. And so in particular, our theorem 2 implies theorem 1. And then in order to construct our secret sharing schemes, we will end up using our lower bounds together with some new ideas. And we'll finish off the presentation by talking about some open problems. So let's get started. So in complexity theory, one of the fundamental questions is how much computational resources are needed to compute some Boolean function? Now, typically, some computational resources that might be considered are time or space, namely memory. Here, we'll be concerned about how much communication is necessary. And indeed, communication complexity concerns itself with how much communication is required to compute such a function. Now here, instead of a computer, we'll replace this object with some all-knowing, all-powerful being. But the trick will be the input will be split across two such beings, and they must work together to compute the output of the function. Okay. So in particular, we'll reset n to n over 2 just to make things nice to work with. Okay, so the rule is they're allowed to communicate 1 bit per round, and they should work together until they both know the output of the function. So the communication protocol might look something like this. And then eventually, one of the players is going to know the answer to the function, and then they can just tell the other player what the answer is. So the communication complexity of a function is just how many bits must be communicated in order to compute such a function. So a natural question is, how can we generalize this model to more than 2 players? Well, perhaps the most natural thing to do is simply split the input evenly across all the players, and each player is holding an input, and they can only see what's in their hand. And again, they will be communicating 1 bit per round, but this time it will be written on a public blackboard that everyone can see. Okay, so the communication might look something like this. Right, where at each round, one person is using what they're holding to write a bit on the board. And eventually everyone's going to know the answer to the function. And this model where a player is given a piece of the input and they can only see what they're given in their hand is appropriately called the number in hands model. And the communication complexity with respect to NIH protocols is what you'd expect. Is how many bits you need to communicate in such a protocol in order to compute the function. Yeah, but there's another way to kind of generalize this model to more than two players that is relatively common. And here, instead of each player being given an input and only being able to see that input, they're given an input and they can see everything but the input they're given. Metaphorically, it's written on their forehead. And here, the communication protocol might proceed like this. So maybe player 4 starts by writing a bit on the board that depends on all of the inputs written on these foreheads. And so the communication protocol might proceed in this manner. Eventually, everyone will know the answer to the function. And based on the metaphor I described earlier, this is appropriately called number on forehead protocols. And the communication complexity in this model is, again, what you'd expect. But note that the way I describe this number on forehead model, where each person can only see what's written on everyone else's head, is actually the same thing as each player being given an input, being able to see what they're given, and then each round, not one player is working to write a bit on the board, but n-1 players are working to write a bit on the board. Right? So instead of the protocol looking like this, where player 4 is writing a bit on the board dependent on these bits written on their foreheads, it looks like these 4 people, or these 5 people are writing a bit on the board based on the bits they're holding. And so this is an equivalent way to describe NOF protocols. And again, the definition of communication complexity in this model has not changed. But the nice thing about this characterization is it lends itself to a more general definition of multi-party communication complexity. And this definition is as follows. So each player receives a part of the input. They can only see the input that they receive. Each round, one bit is written on the board. And then depending on whether you're in the NIH or NOF setting, a different number of people can collaborate per round. So in the NIH setting, one player can collaborate per round, while in the NOF setting, all but one player can collaborate per round. So this is much more powerful. And in particular, as you'd expect, the communication complexity of a function will always be, upper bound in the NOF sense, will always be upper bounded by the NIH communication complexity because n-1 players is much more powerful than one player collaborating. So this lends itself to a natural question. What if we allow some number of players in between 1 and n-1 to collaborate per round? And this is exactly the definition of BCP protocols, right? And so we can milk this animation one final time, to display what a BCP protocol will look like, with P equals 3 here, right? And as you'd expect, the communication complexity in this model, same thing as before, except now you're asking, how many bits must be communicated by a BCP protocol with collusion P. So P people colluding at each round. Okay, so these things were introduced by Kumar, Meka, and Sahai in 2019, and they induce a very nice spectrum over communication complexities, right? So as the collusion goes from 1, NIH, to n-1, NOF, notice that the complexity can only decrease, right? Because more people are collaborating, it's going to be easier to compute this function. And so it's interesting to ask, for those intermediate P, what do the complexities look like? Can we establish some sort of trade-off? Okay. So now that we know what BCPs are, we're ready to start talking about our main results. So we'll start with theorem 1, our explicit lower bounds against BCPs. We'll provide some background and motivation for these, and we'll state our result, and we'll provide a sketch of the proof. We'll do the same thing for our leakage resilient extractors against BCPs, so the proof sketch will be less detailed, and we'll do the same thing for secret sharing. Okay, let's begin with our explicit lower bounds. So why is it a good idea to pursue communication lower bounds in general? Well, it turns out that communication protocols are a relatively simple, concrete model of computation. And, they're kind of more information theoretic and much more concrete and cleaner than things like Turing machines. And they lend themselves very nicely to nice combinatorial interpretations. And so in particular, they're very related to things like discrepancy. And so even though these protocols are relatively simple and straightforward to describe, they seem to be rich enough to capture other models of computation, and therefore they're pretty applicable. So we know NIH lower bounds give streaming algorithms lower bounds, for example. And we know NOF lower bounds give circuit lower bounds. And in particular, any drastic improvement to existing NOF lower bounds will provide breakthroughs in circuit complexity, which is some great motivation, I think. So it's natural to ask, how do BCP lower bounds fit into this picture? And in particular, can we establish some sort of collusion complexity trade-off that's meaningful? Maybe it could provide some more insight into these questions, or find even new applications. So our first result is exactly of this form. We show that there exists an explicit function that achieves the following collusion complexity trade-off, where the collusion bound is P. And I won't force you to parse this. Maybe the most interesting settings of P are as follows. So most notably, even as P approaches NOF collusion, we obtain a lower bound that is still polynomially large. And so in particular, this is probably the most interesting setting of P. And previously, for this setting of P, all previous lower bounds became trivial when the number of parties participating exceeded log n. All right, so let's provide a sketch of the proof. The main idea here will be to take existing NOF lower bounds and use them to create BCP lower bounds, these more general BCP lower bounds. And we'll do this in a non-black box way. So the particular function that we'll use is a finite field multiplication function. Now this function is very simple. It just takes its inputs, treats them as elements of the appropriate finite field, multiplies them all together, and it has to output something. So just take the first bit, it's fine. It has to output one bit, so let's just take the first bit. Okay, so in 2013, Ford and Goyal showed that this very simple function has NOF lower bounds that match the best NOF lower bounds we know. So it will be very nice to work with. So in particular, by definition of this communication complexity that we've seen earlier, this means that if you have some protocol that's computing finite field multiplication with probability 1 over sampling a uniform input, it must be using at least this many bits, right? That's the definition. Okay, so the main goal, again, is to lift these NOF lower bounds to these more general BCP lower bounds. All right, so let's describe the proof here. So the first step is to show that it's actually totally suffices to just show lower bounds against non-adaptive BCPs. And you'll have to take my word for this, but it's relatively straightforward to show and greatly simplifies the proof. So what does a non-adaptive BCP look like? Well, each bit that's written on the chalkboard doesn't depend at all on what was written on it before. And so these things are just deterministic functions of some inputs held by some parties. Okay, so the next step that we'll do is we'll make the observation that finite field multiplication is self-reducible. So what does this mean? So let's start by assuming we have some protocol that perfectly computes finite field multiplication. We'll want to use the self-reducibility of finite field multiplication to show that this implies that it computes some smaller finite field multiplication. And we'll be able to lift lower bounds in this way. So how do we do this? Well, note that just by definition of probability, if you fix the first and second input, this probability will also equal 1, right? But now we can use self-reducibility of finite field multiplication. In particular, this conditional distribution simply yields a smaller finite field multiplication call on the unfixed inputs, right? Because finite field multiplication is just taking the product of its inputs. So multiplying by 1, it reduces to a smaller version of finite field multiplication. And furthermore, this conditioning turns this protocol into a different protocol, pi star. What does it look like? Well, it's the same as before, but now all functions that depended on x1 or x2 look the same, but are restricted to have these inputs fixed to 1. Okay, so looks something like this below, right? Okay, so we just got rid of the conditioning there because it no longer affected anything coming before it. Now, the key observation is that what we end up with, pi star, it will be an NOF protocol as long as in no round did everyone collaborate together to write on the board. Notice that this did indeed happen in this situation. Okay, so we have an NOF protocol pi star, and this probability tells us that it computes a smaller version of finite field multiplication. So this means that the number of bits communicated by the original protocol must be at least n over 2 to big N over 2, or you contradict finite field multiplication lower bounds in the NOF setting. So concluding all that talk, basically what this says is, if you have a protocol computing this function and some T parties don't collude together in any single round, then it must be communicating at least this many bits. Okay, so that's great to know. So the goal now, obviously, is we'd like to find the smallest T possible for which this is true, and this will give us the best possible lower bound. So here's an easy bound on T. We know that we can find the T equals P plus 1, right? We know we can find P plus 1 parties that don't all work together in the same round for any of the rounds, because by definition of collusion P, at most P people work together in any round. This is just by definition. However, using step 2, this immediately gives a nice collusion complexity trade-off. Now this trade-off was known before, but it's unclear whether a proof was written, but either way, these steps are relatively straightforward, and maybe the most interesting step is the next one, asking, can we ever find a T that's much smaller than P? Okay. In order to do this, we'll make some observations. The first observation is that, notice that each round at most P choose T sets of size T all work together and get disqualified, right? Because that's how many sets of size T are in a set of size P. And furthermore, there are n choose T possible sets of size T that could have activated this step. And so if you have a BCP protocol with mu rounds, then as long as mu times P choose T, the number of rounds times the number of disqualified T parties, as long as this is less than the total number of T parties, there will be some T party that wasn't disqualified, namely some T party that didn't all work together in any round. Okay, so we know that there's always some T parties that don't collude together in a single round as long as this holds. And we're pretty much done now. All we need to do is combine steps 2 and step 3, combine these bounds and yield a result. In particular, let's let T be something that we'll pick later. And if we have a protocol pi that computes our function using just mu rounds, okay, let's have a tautology here. So clearly we know that either T parties collude together, or either T parties don't collude together for some T parties, or there isn't a set of T parties that don't collude together, meaning every set of T parties, there's some round that they're all working together. So clearly, this is just a tautology, but plugging in step 2, the first condition becomes either the number of bits communicated is at least n over 2 to the T. And plugging in step 3, second condition becomes the number of bits communicated times P choose T is at least n choose T, right? Because this is saying there isn't a set of T parties. Right? And so we can just combine these with a min statement, right? And this mu is exact, we made no assumptions on pi, so this mu is exactly the communication complexity on their BCPs, right? And now all we need to do is just pick a good T. Trust me, that's a good one. And it immediately gives our result. Okay. And recall that maybe if you don't want to parse it, the spectrum that we obtain looks something like this. And maybe the most interesting setting is this. And previously, all bounds became trivial when the number of parties, got kind of big. Okay, so now we're ready to talk about our leakage resilient extractors. In order to start talking about extractors, we revisit the definition of the communication complexity of a function. Recall that the communication complexity of a function is at least mu if for any protocol that communicates less than mu bits, it computes f with probability less than 1. Okay, so these are exactly worst case lower bounds because of this one here. And so an interesting question is, can we extend our results to average case lower bounds, where here average case means replacing the 1 with a 1 plus epsilon over 2, because they're trivial protocols that compute f with probability half. We'll add an epsilon here to account for this new parameter. This is actually exactly a definition of distributional communication complexity extended to bounded collusion protocols. And in fact, these results come for free from our worst case bounds or without too much work. Okay, so now one might wonder, can we make these even stronger? Well, how can we do that? Note that each X is actually composed of big N independent Xi's, each that's uniform. And so a natural way to make these stronger would say, okay, what if each Xi was not uniform? In particular, what if it only had some guaranteed entropy? The definition of entropy we'll use is not too important to understand the talk, but you can think it's a parameter between 0 and n. N means more entropy. The closer to n, the more entropy, and the easier it will be to get lower bounds. So we want to get lower bounds for as small k as possible. All right. So we'll call such lower bounds average case lower bounds against low entropy distributions. These will be strictly stronger than standard average case lower bounds. So, we'll collapse these Xi's into a single X again, just for notational convenience. You might be wondering at this point, what does this have to do with extractors? Well, it turns out that this expression is exactly the same. This condition is exactly the same as this condition. And what does this condition say? Well, these green bars are statistical distance, and this green U is an independent uniform bit. And so intuitively, the way to see these are roughly the same thing is to note that, if this distribution is close to this distribution and U is independent from this pi is really not computing F at all. It's not correlated at all. Okay. Well, notice that this distribution actually ensures something that you might not have expected, or this condition ensures something you might not have expected, which is F of X looks uniform. And so this immediately harkens to the definition of a so-called independent source extractor, a very popular object in pseudo-randomness, which is exactly an object that, given such a distribution, it outputs bits that are close to uniform, so strictly weaker than this, because this says the bits are close to uniform, even conditioned on some BCP leak on the same bits. So a natural thing to do is extend this classic definition of extractor to handle this conditioning. So a leakage resilient extractor outputs bits that are close to uniform, even conditioned on a BCP leak. So it's the exact same definition as here, just stated as an extractor. And these were introduced in KMS 19 as cylinder intersection extractors. So for convenience, we'll just combine these two boxes. They're the same definition. And we'll no longer use this annoying notation. So we'll remove that from sight. Okay, so this is our definition of a leakage resilient extractor. All right, so we did all this work to cast this problem in terms of extractors. So who actually cares about them? Well, all of these people definitely care about them, but it turns out they have some really nice applications. And the main motivating application is that there are a lot of applications in computer science and combinatorics that use randomness, but these applications require access to uniform bits, and nature only provides us with bits that often have unwanted correlations and biases. And so extractors give us an object that convert ugly randomness into clean uniform randomness. And furthermore, specifically leakage resilient extractors against BCPs, the objects that we're exploring, have found unrelated applications in pseudo-randomness to what we've discussed before. And hopefully they'll find even more in the future. Okay, so this is the definition again that we saw before, just as a reminder. And now that we know what a leakage resilient extractor is, we can state our main theorem. So previously, the best leakage resilient extractor required very high entropy, even just to handle very small collusion. So our first main theorem reduces this entropy requirement all the way down to polylogarithmic in n, so an exponential improvement. And it allows the collusion to grow all the way to 0.99n from a constant here. And then in the extreme setting of number on forehead collusion, we construct an extractor that still outperforms this original extractor, and it can handle just 0.39 entropy. And this is constructed using new estimates on some new general exponential sums. So now we'll go over a very high level overview of this proof here. All right, so the main idea is just bootstrap our worst case lower bounds against this function from theorem 1. As we mentioned, our worst case lower bounds almost for free give us average case bounds because the function that we're using in FG13, they actually proved distributional communication complexity lower bounds on this function. And we can extend the rest of our techniques pretty easily. And in fact, these average case bounds are exactly just extractors for full entropy. So the next step is to decrease the entropy requirement just ever so slightly. And this is possible just by simulating the missing entropy as a little bit of BCP leakage on a uniform source. Our third and final step is to reduce the entropy requirement all the way down to polylogarithmic in n using an object called a low error two-source condenser. And this effectively condenses low entropy distributions into high entropy distributions. And it turns out that our previous analysis can be tweaked to show that this will ultimately be resilient against BCPs. And so our final function, our final extractor is just this here. So it takes the input, it takes its inputs, it condenses them using, some sacrificial source as a common seed to the condenser. And then it just puts them into the finite field multiplication function. And that's it. Okay, so that recovers our leakage resilient extractors. So now let's talk about our leakage resilient secret sharing schemes. So secret sharing is motivated by the application of, wanting to distribute some secret among some individuals that you kind of trust and kind of don't. So here's one nice application. Consider two parents that want to establish maybe some family emergency fund, but they want to make sure that their kids only use it for emergencies. In particular, they want to share the password to this fund with their children, but they want to make sure that one person alone can't unlock the safe. Maybe two people can't unlock the safe either, but maybe if three people try to unlock the safe together, it's actually a true emergency and that should be able to. So formally what they want is a secret sharing scheme. And a secret sharing scheme is defined with respect to two functions. So a share function, which shares the secret into big N shares, and it's randomized, and a recovery algorithm, which recovers the secret from the shares, as long as enough people are involved. And so these two functions constitute a T out of N secret sharing scheme if any T shares, so any T people are able to recover the secret with probability 1 over the randomness of this sharing function. And furthermore, if you have less than T people trying to recover the secret, they can't even recover any information about it. So the secret's completely indistinguishable from something else that could have been shared. Okay, and we say that such a scheme is efficient if it runs in time polynomial in the number of parties participating. And these were introduced by Blockley and Shamir in '79, and have since become a very popular cryptographic primitive. And recently, a line of work has looked at equipping these primitives with leakage resilience. And so we say that a secret sharing scheme is leakage resilient against BCPs if it has all these properties as before, but it also has the property that if you run a BCP over the shares, it also can't reveal any information about the secret. And these were introduced by KMS 19. So now that we know what these are, we can state our results. So previously, the best leakage resilience schemes were T out of N schemes, and they could handle roughly logarithmic in the number of parties of collusion, so not too much collusion. Our first result shows that we can construct N out of N schemes that could handle much more collusion. But it's not as good as the general T out of N schemes. But then our next result shows that we can actually construct general T out of N schemes that can handle almost as much collusion. In fact, about T over log T, which is almost optimal because it's definitely impossible to handle P at least T collusion because by definition of correctness, that'll recover the secret. So this is an almost optimal T out of N scheme in terms of leakage resilience, at least, just the collusion bound. So A super high level proof sketch is we're just going to bootstrap our lower bounds once again. And we're going to use a classic paradigm in constructing secret sharing schemes where you just concatenate schemes to inherit properties of both of the schemes that are concatenated. So we'll start with a standard n out of n scheme. We can use the classic XOR-based scheme from KGH83. This will give each person 1 bit or so in their share. Now we're going to equip it with leakage resilience against BCPs. And we'll do this by giving each person some extra randomness in their share, and then forcing one person to compute this BCP hard function on the randomness of everyone else, and then hiding the secret within there. So if you want to recover the secret, you need to compute this BCP hard function. So previously, the best lower bounds on BCPs required this step to add an exponential in P number of extra bits per share. And so this was only efficient if P was pretty small. Our new bounds, however, only require a constant number of extra bits to be added per share, even when the collusion goes up to 0.99n. So from log n to 0.99n. And the final step is to bootstrap this leakage resilient n out of n scheme to get a t out of n scheme. So we can do this by using this previous scheme to create a t out of t scheme for every set of size t. So for example, we can do it for this set and then maybe add some junk extra uniform bits over here to even things out. And then we can create another scheme for this set, another scheme for this set, and so on. And this will work, but the problem is that the shares will now grow by a factor of n choose t, which is roughly big N to the t. And this is not efficient when t becomes super constant. So the idea in KMS 19 was to use this reusing share idea from the 90s with perfect hash families to reduce this factor to 2 to the big O of p, which is much smaller because p is less than t. But this is only efficient when p is logarithmic in big N, and we'd like to allow for much more collusion. So the key idea in this work is to use a weaker type of hash family called ramp hash families. And this allows us to reduce this factor all the way down to just polynomial in big N. As long as p is at most t over log t, p definitely can't be bigger than t, so this is almost optimal. So this recovers our secret sharing results that we discussed earlier. Now we'll briefly recap our results. So first, we established explicit lower bounds against the entire spectrum of BCPs of this form. It'd be interesting to see if you can get better lower bounds, perhaps not by bootstrapping off of NOF lower bounds. Next, we constructed leakage resilient extractors against BCPs that work for just polylogarithmic entropy. In the NOF case, however, our extractors require quite a bit more entropy, and it seems like this case is much more difficult. So it'd be interesting to kind of reduce this entropy requirement down to polylogarithmic in N, or maybe even just sublinear in N. And finally, we constructed several leakage resilient secret sharing schemes that can handle an almost optimal amount of collusion. And we have very general T out of N schemes. We also construct more general objects in each of these settings. We encourage you check out the paper for the full results. And here it would be interesting if we can reduce the gap between P and T. P can't be T or greater, but it'd be nice to get this to maybe 0.99T or something to match this. And two general interesting questions to pursue might be, are there any natural applications of leakage resilient extractors in pseudo-randomness or complexity? We know that there's already at least one application completely unrelated to what we've discussed in pseudo-randomness. And it'd be interesting to see if there are any applications of leakage resilient secret sharing in cryptography, perhaps in constructing leakage resilient multi-party computation protocols. That concludes my talk. Thanks for stopping by. Hope you enjoyed.